Dilute magnetic semiconductors is the one of the category of magnetic material, and in previous lectures I have sounded about it that uh, we have seen different types of magnetic materials. So technically, all materials possess some sort of magnetism. This is how the research community describe magnetic properties of material. Either they are diamagnetic, paramagnetic, or ferromagnetic. And now many other categories are added: semiconductor, superconductors, dilute magnetic semiconductor, etc. So, in order to understand dilute magnetic semiconductor, what we have to do is that uh, we have to take a semiconducting material and dope it with some materials like Mn2 plus or Cu2 plus impurity, which are at the level of 2 to 6% pyruvate. And uh, the semiconducting materials like gallium nitride, gallium phosphide, or zinc oxide with doping of Mn on Cu can create uh, magnetic field, and that is decided by the hole concentration and the temperature. So the example is shown the schematic plot of dependence of Curie temperature of a dilute magnetic semiconductor on hole concentration. So we can see that below Tc, the material semiconducting material is ferromagnetic. Above Tc, it goes into paramagnetic domain, means it shows less magnetization. And the device made up of such a dilute magnetic semiconductor is shown as a uh, memory device. So how it is done? That normally uh, gallium phosphide is implanted with some ions with a beam of 250 keV of Mn ions, and this method is usually means usually applied in production of various diodes and transistors. So normally what happens that the Mn ion sits inside the matrix of this gallium phosphide, and it donates its two of the electrons and thereby creating holes, and these holes possess the magnetic property. But there is a one more simpler method is applied, that is called a sintering method. So in the sintering method, what is done, or solid state reaction method, where uh, MnO and gallium phosphide are mixed in the ratio of 0.03 of the molecular weight of MnO to the molecular weight of gallium phosphide. So for one molecular weight of gallium phosphide, 0.03 molecular weight of MnO is added, and this material or mixture is finely ground for many hours using mortar pestle, and then pressed into a pallet. So it is like a tablet shaped pallet. The pallet is then heated in aluminum oxide board called alumina, up to in a oven with around 500 degrees for 4 hours, and then uh, after heating, so this is a process where you can create semiconducting dilute magnetic semiconductor using sintering method. So once it is done, then the hot pellet is quenched into uh, water or some cooling medium to room temperature. Now the gallium is plus 3 ion and Mn is plus 2 ion. Doping with the manganese will create hole doped material, and this hole doping can obtain from now. So this is a process from here, which is solid state method of designing the DMS, dilute magnetic semiconductor. How to identify whether this hole doping is successful or not? That can be understood by the Raman spectrum analysis. So Raman spectroscopy shows that the Raman spectrum of transverse optical mode with a lower frequency mode and the longitudinal optic mode, which are higher frequency mode, in undoped GAP and MN doped GAP. So 40.16, this is here. So one can see that there are two modes, the lower frequency and the higher frequency mode. And uh, the larger spectrum is for undoped, pure. And this one is the doped one. So the smaller spectrum is for the doped one and the larger spectrum is for the undoped. So undoped, what it shows that Mn2 plus doped GAP has a reduction in the intensity and the doped one has a large intensity. So this Raman spectrum is associated with the availability of the free electrons or conduction electron and the plasma frequency of these electrons. Okay. So these are the plasma modes. Uh, Now the frequency of longitudinal optic mode is shifted to down in the doped material. This is the one observation. This is because this longitudinal optical mode is coupled to the plasma mode. Okay. And plasma mode is a collective vibration of the conduction electron. So what is this? This is a collective vibration of the, this is a technical information with its frequency proportional to concentration of conduction electron. Okay. So the more number, the frequency will be more. If the electron concentration reduce as a result of hole doping, right, means some hole will recombine with the electrons and therefore they will reduce the number of electrons and there will be majority of hole. So plasma frequency will automatically reduce because it is associated with the number of conduction electrons in the optic mode frequency, and there will be slight shift from its central position. So this way the Raman spectrum can confirm that the hole doping is successful. This is the one indication. Then if this material is subjected to magnetic field uh, and its susceptibility is measured at different temperature, then different results can be obtained. So one can see at 300 Kelvin, means at room temperature, you get this spectra, and this is at 5K. So at lower temperature, this dilute magnetic semiconductor shows very high hysteresis loop, and this shows a lower hysteresis loop, means lower susceptibility. That also one can assume. So magnetization, that we have seen that there are some property like chi. It depends on it is a property of say applied magnetic field. So we will write H here, and also the it is a property of a temperature. Okay. Similarly, when the susceptibility depends on the applied magnetic field and the temperature, there will be MS and coercive values that also depends on the uh, temperature and the applied magnetic field. That is one thing. Then the magnetization is also dependent on the particle size. Okay. So M is nanoparticle size dependent. So this is small d. So magnetization of a given depends on the dimension of this dimension of the nanoparticle. So we have to focus on what we want to understand. That chi depends on the applied magnetic field and also the temperature. The temperature decreases. The for certain materials, you will see the high values of the hysteresis loop, and also you will get high values of susceptibility. At the same time, uh, there is the effect of particle size since it is in nano domain where the mean free path is further bigger than the dimension of the nanoparticle for the electron. And here, the surprising thing is that uh, in case of semiconductor, the holes are contributing to the magnetization. So that we have to always remember. So purity and ferromagnetic resonance showing the materials is ferromagnetic. So at room temperature, ferromagnetic resonance measurements were used to study ferromagnetism above room temperature and Curie temperature determined to be 600 K. So this material still shows magnetization with a less effect, but the Tc is 600 K, means above T 600 it will lose its magnetic property. So it is required a dominant interaction of produced ferromagnetic ordering is the exchange. So the dominant interaction that produces ferromagnetic ordering is the exchange interaction that we have seen previously, and this is short range nearest neighbor interaction between the spins of the paramagnetic. Now, in order to understand the mechanism of the ferromagnetism inside this doped semiconductor, uh, is that the possibility is Mn ions which are doped in the semiconducting materials are not dispersed. They are not uniformly dispersed in the lattice, but what they do is they form a nanoclusters or small clusters which are ferromagnetic in nature. So this is a phenomenon. Whole number of hole increases. Also, when the manganese is dispersed in the material using sintering process, the manganese forms a cluster, and these clusters may have a different sizes. And then the size dependent magnetic property is given to the particular semiconductor. So this way, it try to solve the issue that the cause of magnetization or magnetic property in the semiconductor is because of nano structuring of the image. Okay. So MN clusters are observed to be ferromagnetic. There is a one more thing is that these MN clusters to be ferromagnetic only at lower temperature and thus cannot account for observation of permanent ferromagnetism above room temperature. So again, means there are some technical issues or technical queries like MN clusters basically show ferromagnetic nature at lower temperature and not at room temperature. But when they are doped in this semiconductor at room temperature also they show ferromagnetic behavior. Some copper doped GAP also observed to be ferromagnetic since there is no known evidence of ferromagnetism in copper cluster. This suggests that such clusters are not the origin of ferromagnetism. Means at one side the Mn shows magnetization ferromagnetism for a very smaller cluster below lame temperature. At the other end, copper itself is a diamagnetic in nature, and nanoparticles of copper embedded or doped inside gallium phosphide shows magnetization or ferromagnetism, but individual copper clusters do not show ferromagnetism. So, uh, this is how the knowledge means the traditional knowledge is being changed at a nano level. Uh, okay. So, and therefore there need to be more study in this field. So the explanation of ferromagnetic in dilute magnetism is still a matter of research. This is how it is rendering the problem that how this dilute magnetic semiconductor shows ferromagnetism, though the constituents are not magnetic in nature. Either they are not paramagnetic or not ferromagnetic. They are diamagnetic in nature, but they are when the nanoparticles are doped in this material. So material-material interactions are changing the magnetic property. And now such doped materials can be produced in the form of a thin film, and the magnetic properties of such thin films can be studied. That is the one thing. So the bulk material do not show magnetization, but nanofilms can show some sort of magnetization, and new science can emerge from that. That is the one thing. Now, what is the use of DMS is that it can be basis of magnetic storage device. So the idea is that use them as a electrically controlled magnetic switches. How one can do it is that uh, there is a metal gate, there is an insulated amine doped semiconductor, one doped semiconductor. So this is the switch is used where this portion is doped with amine. When the positive voltage is applied, um, the holes are pushed into the undoped semiconductor layer, and the doped layer become non-ferromagnetic. So this is ferromagnetic layer. When you apply positive voltage here, what will happen? This positive voltage and its field will push the holes into undoped semiconductor. Thereby, this will become non-magnetic, and uh, this will remain as it is. And when you apply very small negative voltage, at that time, what will happen? That the layer becomes again ferromagnetic. In this effect, the small voltage can control the existence of ferromagnetic ordering in device. Such device can become basis for magnetic storage device. So this methodology can be used to store the data in the form of 0 in 1 for the magnetic storage device, and that can be then read from the reading head. Uh, so this can be act like a uh, um, memory storage. DMS switch can be act like a digitally controlled data storage device, and the data can be read from the uh, magnetic properties rendered by this amine of semiconductor. Okay. Also, the magnetization can also be affected by light. Right, means when the light is shine on this, the field of light can also um, magnetize or demagnetize depending upon the frequency this amine dope semiconductor. So there are two possibilities. One, by using the applied voltage, one can change the magnetization state, or using light also one can change the magnetization state, and it renders two possibility of using the device as a data storage. Then there is a one more category called as molecular switch and electronics. So how the molecular switches are using? Our MOSFET, the solid state MOSFET, may not work below 10 nanometer dimension because whatever kind of doping profile you have, the dimensions of gate will be larger, uh, and they have some threshold value. So you cannot make it gate dimension smaller than that. And if you reduce overall dimension of the transistor, the drain dimension and the source dimension will reduce, but the gate dimensions will remain as it is. And therefore, this kind of device may face difficulty and lots of heat dissipation uh, while the operation. So people started looking for different materials, and to reduce this, people found out that there are certain molecules that display switching behavior. Means they can be conducting and they can be non-conducting. That is the switching behavior on certain conditions. So these molecules can be conducting or non-conducting depending upon the light falling on it, or uh, depending upon the voltage applied to it. So this can be used to create storage and logic circuitry in the computer. A molecule that can exist in two different states, such as two different conformations, and can convert it reversibly between two states by external stimuli. Okay, where you can use light or voltage can be used to store the information. For that purpose, one state of the molecule can be considered as a zero, and the other state can be considered as a one using binary logic. So then these states of this molecule can be understood from the uh, certain read and write probe, or using different modes. Now, first see what happens to the molecular switch. So there are certain molecules uh, which can be converted from cis and trans. So these molecules have a isomerism, and can be optical isomerism. So optical isomerism, where they rotate the plane of uh, the light, plane polarized light into circular rotation. So you can have the light falling on the particular molecule, and it is rotating the plane of the light in a clockwise or anti-clockwise direction, and that will be decided by the isomerism property of the molecule. So in one case, and the molecule will be have a state, either it is a cis or trans, and then once the light falls on it, it goes into trans state. So how it is achieved? That when the light of 330 nanometer falls on it, it changes the molecule from trans isomer to cis isomer by subjecting the 313 alpha. Means from trans, it goes into cis transformation, and it can be returned to original when exposed light wavelength greater than 330 nanometers. So there are two wavelengths. This is ultraviolet and this is visible light, 380 nanometers, more than that. So by using two light pulse, you can change the state of this trans and cis isomers, and thereby you can change the conductivity if they are connected with a electrode. So what will happen that such molecules can be used to store the data, and by just shining the light, you can change the information stored in that by means of using 313 nanometer ultraviolet light and 380 nanometer light. And the dimension of this molecule is very small. It is smaller than 1 nanometer. So the memory density of such device will be very high. Only the problem which people face in such is that a form of azobenzene is not thermally stable, and slight heating can cause it to return it to transform. So um, in normal case, you want to transfer the um, azobenzene molecule from cis to trans, you require energy greater than 380 nanometer. But when there is a direct supply of it because of the high temperature, then it can change and therefore it becomes unstable. So there are chances that people may find out some different molecules where they are not affected by the temperature, or some sort of mechanism must be applied where the temperature of this memory device cannot rise. And there are some Peltier cooling device uh, which can cool down the material by passing electric current from the Peltier phenomena. So, combination of these two can give rise to a very dense memory device. So, this is a example how it changes the trans isomer and the cis isomer. So, this is azobenzene, and when the light forms of 330 nanometer, the trans isomer changes into cis, and it comes to original position. Now, using light and this kind of arrangement, this system can act like a transistor or a switch. So when it is in transform, the molecule is having higher length and it is extended. So it is conducting, suppose this is connected to some electrode from here to here. So this is in contact. Okay. So now it is conducting. When the light of 330 nanometer falls on it, it will get uh, compressed, or it will shrink, and because of which it will disconnect this metallic connector from the other electrode, and therefore the switch is open, and this way you can close the button. Now you shine the wavelength greater than 380 nanometer and it will come back to the conducting state. So using the light signal you can make this transistor work, and this can be optical switch. So this is how people thought of creating transistors using molecules which are very small, and using transistor now you can design logic gates. Logic gates are used in IC for the fast processing, and these molecules are not generating tremendous heat compared to the semiconductor. So this is one of the domain where, or one of the area where people are doing more research. Now there are different types of molecules where they can be used as a data storage device. And here, this is a chiroptical molecular switch. Now, what it does is that one can use circularly polarized light to change the isomerism. Means it can be rotated from cis to trans, okay, by using circularly polarized light. Now, to read the information, what means, what is the state of this, you have to shine the linearly polarized light. So that will, because of the rotation, it will rotate the light, and depending on the right-handed rotation or left-handed rotation, one can understand that this is showing 0 or 1. Okay. And if you want to erase this information, you can just shine unpolarized light. So what you have is that circularly polarized light. It can be right-handed or left-handed circularly polarized light. To write some state on it, to read, you require linearly polarized light, and to destroy the information, or to format the memory system, you require unpolarized light. So using three types of light, means same color but different polarization, that can be used to store the data into this chiroptical molecule. So there are some examples which are given here, which are having similar. Some of them are conducting in one state, some of them are not conducting in one state. So molecular electronics is the part where the molecule shows conduction of electrons, and this was studied using STM, which is the tip of the STM is coated with gold, and this gold provides very good interaction with the molecule. For certain molecules, the gold provides very good interaction, and thereby when you apply proper bias to the tip, the gold can donate one electron, and at certain voltages, and because of which the molecule will become conducting. Then you increase the voltage. Again, the gold will donate one more electron, but now the conductivity of this gets reduced, even though the addition of extra electron, and because of which uh, this will give rise a step conduction. So this is I and this is V curve. So here you will observe the step of conduction, means it is conducting. When you add one more electron, it will not conduct, uh, or it will jump to some higher state. So current can be reduced. This will be like this. This is conducting, you increase the voltage and this goes down. So at with one electron at this level, so when you increase some voltage, the electron is added by the gold metal and the molecule is conducting. Then you increase the voltage above which again it will reduce the conductivity. Okay. So this is the switch that can be used, and gold can be used in this. Now this is a one type of molecule. We don't need to remember the structure. This is rhodaxine. So you can just represent that it has a two ends which are like A and B input, and there is a output Y. Okay. So this molecule behaves like a logic gate, A, B, and Y, and this has the operation of Y is equal to A dot B. So this particular molecule behaves like a AND gate. So when you apply voltage to A and B, then you will get some output voltage or current flow at the Y gate. And this molecular switches may give rise some different logic combinations which are not present in the other semiconducting materials. So to use this molecule as a logic gate, this scheme is shown where you have a silicon oxide Si substrate on which aluminum is deposited as a metal connector for output. Then there is the insulation Al2O3. Then there is a rotation monolayer. Then the titanium and aluminum is deposited, and this particular switch is developed. More details are not given, like which is A input, which is B input, and which is Y. Okay. So upper electrode has a layer of a titanium, and the lower one is coated with aluminum oxide. So this is how it is shown, but the function is not there. Only thing is that when the switch is closed, the current is flowing in the amperes. When the switch is open, the current is zero, and when the voltage is negative, the reverse negative current is flowing through the switch. So this is just an example. And one can see that in this case, the current flowing through this is when A is 0, B is 0, the 0 amount of current is flowing. Then when 0 and 1 is given, there is a slight increase in current. When it is altered 1 and 0, the current value further increases. When 1, 1, 1, this is the high amount of current. So normally this part in our semiconductor logic gates is considered as zero domain for 0, 0, 0, 1, 1, 0 condition, and only 1, 1 condition gives you one output. But here, this AND gate represent different current values, and now from the current values you can see there are four logic levels. 0 and 1 is there, and there are two intermediate levels. So if one can define the intermediate levels between 0 and 1, then there there can be a generation of some new Boolean algebra for this kind of molecular logic. So the main thing is that how the current passes through the molecule or electrons flow from the molecule. The mechanism is very simple. There are two levels in the molecules. One is called as homolayer, which is sort of a valence band, highly occupied molecular orbitals. So, like atomic theory, hydrogen atomic orbital theory, in case of molecule, the quantum mechanical theory used is molecular orbital theory. And using this, the name of this valence band is replaced by highly occupied, HOMO. So highly occupied molecular orbitals, and there is a band gap, and then you have a LUMO, low unoccupied molecular orbitals. So these are the orbitals which are not occupied. So when you energize these HOMO orbitals, electron will gain energy and jump into the LUMO. And when it goes into LUMO, this becomes conductive. Okay. So this is a simple phenomena with an analogy with a valence band and conduction band. So different energy levels are there. And the molecules are excited. The electrons from molecular orbital jumps into the LUMO domain, and they can go to the conduction. They can give rise conduction. So let us see this last part of this topic, photonic crystal. This is the important part. Photonic crystal consists of lattice of dielectric particles. That is the one thing. So they are the name photonic and crystal. So they are crystal structure which are having lattice arrangement, a periodic arrangement. But these are dielectric particles, not the single atom, but some of the dielectric particles. And the separation between these dielectric particles is of the order of wavelength of visible light. In case of our normal crystal structure, the atomic structure or atomic separations is of the order of wavelength of X-ray. Here it is of the order of some wavelength. With such crystals have interesting optical properties. So, what are these properties? Before that, we will see uh, how the light is reflected or reflection of waves of electron in ordinary metallic crystal lattice. So, you have a given metallic crystal, the way X-rays are reflected or the way light is reflected. So, the electrons can also the means the waves associated with electron can be reflected by metallic crystal lattice. So what happens? So the wave function of an electron in a metal is given as a free electron wave function. Means the electron is no longer bound to the individual atom. It is bound to the given metal existing. And that's why it is considered as a free electron. So this is given as psi k of r equal to 1 upon v raised to half e raised to I k r. Here the v is volume. This is important. This is volume of a solid. And this the momentum of the electron is given by p is equal to h cross k, and k is a wave vector which is related by this relation. So this is all well understood things that we study in quantum mechanics. That v is a volume, momentum is p is equal to h cross k, k is associated with lambda, lambda and k and lambda is given by k equal to 2 pi by lambda. So now in nearly three electron model of a metal, the valence or the conduction electrons are treated as non-interacting free electrons. Because in a metal, there is no band gap mainly. Uh, so that band gap theory actually gives you three types of material: conducting, semiconducting, and insulating. Now here the electron jumps from valence band to the conduction band very easily because of absence of band gap. Secondly, this electron is not associated with individual atom. This is associated with the what we can say the material, and therefore what will happen? This uh, electron is treated as a non-interacting free electron in a periodic potential. So this potential is arising from the positively charged ion core. Okay, so this group of ions which makes up crystal structure, which are positive, and the outermost electrons have already left the atom, this ion cores will create its own periodic potential. And when you do the plot of energy versus wave vector for one-dimensional lattice of the ions, the energy is proportional to the square of the wave vector. Okay. So energy versus wave vector for 1D lattice, the energy is proportional to the square of wave vector. That means it is equal to h cross square k square upon 8 pi square m. And near the band h, k equal to plus minus pi a, where it is changing. Okay. So the means it becomes infinite. So to important result, that is there is an energy gap of width Eg, meaning that there are certain wavelengths or wave vectors that will not propagate. So here you can see in a given ionic system, the energies associated are given by E equal to h cross square k square upon 8 pi square m. But there is a some sort of boundary condition at pi a, where there is a energy gap, and then it jumps to the second allowed band, okay, for the different value of k. So what will happen? This is a result of a Bragg reflection. Means uh, Bragg reflection that we have seen in case of X-ray, that n lambda equal to 2d sine theta. That is the condition which has to be satisfied. Okay, so and these are the interplanar arrangements. And when you go from one plane to another plane, there is a some gap, and only waves which are multiples of this particular uh, interplanar length will be reflecting. The rest of the waves will die out. This is what happens. So what will happen here, that this energy is not continuous. There is a sudden change in the energy. So this is a forbidden region. Now this forbidden band can be used in a different fashion. One is that it can act like a filter. Means you certain wavelengths that you don't want, that wavelength domain. So you can create some ionic crystal structure such that it will have this forbidden band gap which is matching with certain wavelengths, and these wavelengths can be omitted. Like in microwave, you want to communicate with only certain frequencies. So these frequencies can be selected using this kind of crystal. So they certain wavelengths or wave vectors will not propagate in the lattice. So from this to this, these wavelengths will propagate. Means this energy is shown. So the wavelengths with this energy can propagate. Then this is forbidden, and this will not propagate. So what is going to happen, that this distance containing the separation of the atom by distance d, and will give rise a path difference between the two waves reflected from the adjacent plane. So this is a Bragg condition, that n lambda, normally the first order, n is the order of reflection, n, so lambda equal to 2d sine theta. Okay, so when the path difference is matching with the dimension of wave, then and then the wave will be propagating or it will be reflected. So theta is the angle of incidence of the wave vector or a wave of the plane in a path different 2d sine theta half wavelength. What will happen? Now there is a one more condition. Since the waves are sinusoidal in nature, if it is half wavelength, then uh, one has to study optics very carefully. The wave is falling from rarer medium to the denser medium. Its phase does not change. The phase goes as it is. From the denser medium, it goes into rarer medium. The phase is altered by 180 degrees, and because of which, what will happen? Suppose this is N1 and this is N2. this is greater than this. Means N1 is the refractive index, which is say air, and N2 is the refractive index of water. Say. So from rarer medium to denser medium, if wave is going, it will not change its phase. But suppose the wave is going in opposite direction from water to air, then what will happen that from denser medium it goes like this, but while coming out again it will acquire the phase reversal. Okay, and that's why we have seen that when we see the mirror image, when we see the reflection, it is reverse. Means our right hand appears like a left hand, and our left hand appears like a right hand because light from rarer medium goes inside the mirror. There is no phase reversal. It gets 100% reflected from the coating on the back side of the mirror, and from denser medium it comes back to the rarer medium. At that time phase reversal of 180-degree takes place. So this is the important thing one has to understand. Okay, so from rarer to denser, no phase reversal. From denser to rarer, there is a phase reversal. And if the part difference in this case is half wavelength, the reflected wave will destructively interfere and it will be not able to propagate. Means the wave vector will die out because of the half wavelength. So you need to have a selection rule or a matching conditions that the path length must be matching with the distance between the atoms. Also, the path difference must not be half wavelength. So, what will happen that this may be a cause that there will be some energy gap. Means for certain waves, the atomic distance acts like a half wavelength distance, and because of which, due to destructive uh, interference pattern, the wave energy do not propagate in the lattice, and therefore it gives rise to the band gap. This is the result of lattice periodicity and the because of the wave nature of the electron. So by considering these things, uh, this Yablonovich proposed the idea of building lattice with separation such that light could undergo Bragg reflection. So this is the theory of photonic crystal. And now where to use this theory? Let us consider Bragg reflection mechanism for visible light, which is quite impossible uh, to develop. But uh, how it is done is that uh, he has developed certain zero point 0.5 micrometer or 500 nanometer uh, quantum dots, which are well separated with a distance of zero point 0.5 or 500 nanometer. And then the light is shine over there. So this can be crystal have been artificially fabricated by method of electron beam lithography or X-ray lithography. So by masking and the separation between the rod-like structure is 500 zero point 0.5 micrometer is achievable using masking technique and lithography. So what is done here is that you can see this is a material, then there is a gap here. This dark one is the gap. Then again the photonic crystal. Then there is a cavity here. So this is a some sort of a porous multi-layer structure where you have a material which is dielectric constant. Then there is a air, and this is sandwich layer. And this A is reflecting the lattice parameter of such system. So this is a one-dimensional photonic crystal consisting of alternate layers of materials having high and low dielectric constant. So not necessary that this dark one must be the air, but here you can have a N1, N2, N1, N2, N1, N2 kind of arrangement. And we have a ellipsometer in our lab, research lab. So basically this instrument can give you the idea of this multi-layer system. And by solving the data available from that measurement, you can actually calculate the refractive index of individual layers. Means this device measures the overall refractive index, dielectric constant, extinction coefficient of entire material. Now, using the software and get by knowing the observed values, and if you develop this multi-layer means model, then this model can easily tell you what is the refractive index of individual layer that is used in this, and we have some samples which are multi-layer. So we have already done it, and this is more interesting. So these are the photonic crystal whose properties can be studied using ellipsometer. Ellipsometer is a device where it shines the polarized light, and the beam shape is elliptical. So elliptical beam is falling on the material, and this material, this is the shape of a beam which is elliptical and it is polarized light. So when it falls on the material, it undergoes reflection through several layers, and in that process, the direction of this elliptical beam is rotated by certain angle. So if it is rotated by 90 degree and all these things, so psi and delta. So psi and delta is a change in the orientation, and psi is the absorption of parallel and perpendicular component of the light present in this. That will give you the thickness information, refractive index, and all these things. So the experiment measurement will take some fraction of second or 2 seconds. The data analysis can take 1 day or 1 month, depending upon the uh, complex deposition profile. But this is more interesting. So what will happen that uh, when you have this multi-layer coating with different refractive indices, these photonic crystals can behave like crystal structure with a different diffraction property in a visible light domain. Okay, so when the wavelengths of light ranges from 200 to UV 900 nanometer, and photochromic crystals are developed with around 500 nanometers. So what will happen that only a particular wavelength and will be selected and it will be diffracted. So like prism or a grating where you can see the dispersion of light. So when the white light shines on the photonic crystal, by knowing the angle of incidence and by solving the Bragg's condition, you will be able to find out, or you will be able to select a wavelength. So again, you can use the lambda equal to 2d sine theta on such crystal. So lambda will become the uh, function of angle of incidence, and the thickness, since thickness is kept constant, so lambda will be function of the angle of incidence. So the description of behavior of light in photonic crystal involves solving Maxwell's equation. So we will just see what is this Maxwell's equation. So the equation is del square h of r plus epsilon the omega square upon c square h of r. So here h is the magnetic field, omega is the wavelength, epsilon is the dielectric constant, c is the speed of light. So h is the magnetic field associated electromagnetic radiation, and epsilon is the dielectric constant. So from this relation, uh, the it can be solved for this photonic crystal because epsilon is associated with the dielectric constant of the material. And since there is a little interaction between photons and uh, with the material, the predictions can be very accurate for the dispersion relation. That is nothing but what will be the speed of the given wavelength within the this kind of photonic crystal. Now, one can assume some solution. We will not go into much detail of it. So, UZ is a periodic in layer separation, that is UZ equal to UZ plus NA, and where A is the period of the layer. So, the magnetic field is given in the form of the solution is given in the form of UZ uh, exponential ikz, and uz is nothing but it is a periodic in nature. So this is uz plus na, where a is the period of the layer. And once you submit, you will get some sort of this dielectric constant dependent dispersion relation. Okay. So actually, what we have to understand is that when we have a alternate dielectric constant layers in a given photonic crystal, there is a frequency region where light cannot propagate. So for this kind of photonic crystal, certain frequencies cannot propagate, and this result referred to as a photonic band gap. Okay, means uh, now there is a directionality dependence of propagation of light. Okay, so if the light is falling from the top, it may get reflected, it may get selected, and uh, certain frequencies will be reflected, certain frequencies will be absorbed. Okay, so that is the one thing. If the light is falling in this direction, what will happen again? Certain waves will propagate only in this direction. Okay, so there will be relation that when the light is falling in a normal incidence, the light which is reflected now will not travel through this band gap. Okay, it will get scattered, but the light which is prohibited or because of the band gap, so that photons will get trapped and they will only move through this as if it is a optical waveguide. Okay, or it is like an optical fiber. So because of the change in the dielectric constant means change in the refractive index. So that is the main basis of uh, uh, optical fiber. Now there is one. There is a um, the optical fiber has got limitations. You cannot bend the light in 90 degrees, right? There are some bending losses. So you have to have some limitation of the light propagating through the optical fiber. But for the photonic crystal, people have seen that light can go directly and it can bend at 90 degrees. Means there is a sharp bending of light, and the area where you require such sharp bending of light, you can put this photonic crystals so that light will go like this and it can come out with a 90-degree of reflection without loss. And instead of that, if you use optical fiber, there will be a bending loss. There is a absorption of light in the material. So many kind of scattering loss, absorption loss, bending losses will come in this. But however, you have carefully developed this photonic crystal, so you can avoid the losses of bending, and also you get desired operation in a very well manner. So that is the use of this photonic band gap for such kind of crystals. So again, in this case, photonic band gap. So one of the idea is that you have some material, and what you do that you remove. This is a one particular material with one dielectric constant. Now you just remove certain area of this material. So what will happen now? You create a photonic band gap, okay, here, because now what you have done is that this was a uniform material. Now you have replaced this part by means of some different dielectric material. Okay, so you have a N1 here, N2, N1, or you have a epsilon 1, epsilon 2, epsilon 1 kind of arrangement. So actually you are creating a photonic band gap, and this band gap what will happen that within this region, there will be lots of energy or photon energy or light energy is there. And here the light energy is zero for that particular wavelength. This is the frequency dependence parameter. So this way the light power is intense below the band gap and like conduction band and valence band, and this region is called dielectric band. So above forbidden gap the light power is low and region where it is referred as a air band. So this is the one of the example of uh, photonic crystal where these rod shaped materials are developed. They are having some dielectric constant and the gap is air gap. So air has a refractive index 1 and it has a epsilon naught as a predefined value. So such photonic crystal can uh, act like a very good microwave selector or a optical wave selector, and uh, the power dissipated in absorption is reduced in such photonic crystal. So they are useful. So and then such devices can be used for generation of laser by making this rod-like structure uh, to do fluorescence. Means they will absorb the certain energies and again they will go into excited state, then metastable state, and they will release the photon. Now this photon will excite the another rod which is in excited state, and you can have several rounds of light from left to right or front and back. And for the semiconducting material, you don't need to apply specific coating. Only if you make one side rough, like this part, if you make rough, this will act like 100% reflecting mirror. So photon will come here in this direction and it will reflect back. Here you will have to apply certain coatings which can be 80% or 90% reflecting. And when these photon are trapped in this cavity, they will give rise light amplification or laser, and then the intense beam can be coming out from this photonic crystal. So many use uh, are decided by the structure and uh, the capability of this particular material. So this is all about the nanoelectronics and magnetic and all this part. And photonic crystals are basically used in terahertz range. This domain of light is yet to be explored because what is happening that in terahertz region, all the materials have their own signatures or signature wavelengths. And if you create a database of that, then you can use it in several applications. As I told earlier, that uh, this terahertz particular frequency can penetrate through the wall or it can penetrate through the clothes. And if you are hiding certain metal piece, it can reflect and it can show you that a person is hiding uh, some knife in his clothes, or person is hiding knife in a paper or a gun, or it can be used to detect the drugs also. So this is the benefit of photonic crystals in terahertz. Challenges are detection of terahertz and creation of terahertz. Mainly the production of terahertz is very challenging, and people are able to produce terahertz frequencies, but the intensity is very small. So amplification is needed, and to achieve that, photonic crystals can be one of the solutions.